Hello, this is Erik, and today we'll be talking about the Hill Cipher. The Hill Cipher was invented by Lester S. Hill in 1929 and was one of the first polygraphic substitutional ciphers that used linear algebra to encode and decode messages. What it does is assign a numerical value to each of the letters in the chosen alphabet you choose. For example, A is equal to 0, B is equal to 1, C is equal to 3, and so on and so forth. To encrypt a message, you create a matrix of the message you want to send. An example being the word food. The first value in the 2x2 matrix is F, the second is O, the third is O, and the fourth is D, which equates to the 2x2 matrix of 5, 14, 14, and 3. You will then create an encryption that will encrypt your message, an example being Erik, the first value being 4, the second 17, the third 8, and the fourth 10. To encrypt, you will multiply your encryption to your message, food times Erik, and you will get 132, 225, 80, and 268. You'll then take the module 26, because there are 26 elements in our key. You'll take the module 26 of the matrix, 132, 225, 80, 268, and you will get 2, 17, 2, and 8, which will be CRCI. Now we'll be talking about deciphering our own Hill cipher. As you see, the encrypted message above is stated, which will give us a matrix of 23, 17, 2, 10, 23, 8, 17, 3, 6, 12, 14, and 23. This is a 3x4 matrix. Our encryption key is a 3x3 matrix, which will be broken down into 2, 8, 15, 7, 8, 17, 8, 13, and 6. To find the inverse of the encryption key, you will use Gauss-Jordan elimination to find the inverse of the encryption key. So, as you can see, this is the Gauss-Jordan elimination. We will set the encryption key relative to the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. We will then try to have the left side turn into 1, 0, 0, 0, 1, 0, 0, 0, 1. If you will use Matlab, this is the code that you will use. After completing Gauss-Jordan elimination, you will have the following 3x3 matrix down here. You may notice that the matrix contains fractions, which doesn't make multiplying matrices easy, so we'll need to multiply the matrix by a number or two to turn the fractions into integers. In order to turn these fractions into integers, we will need to multiply the determinant of the encryption key matrix. In order to find the determinant, you will take this math right here. You will have 2 times 24 minus 221 minus 8 times 42 minus 136 plus 15 times 92 minus 32, and the determinant of our encryption key matrix is 1243. This is the Matlab code for the determinant of our encryption matrix. After multiplying, you will get the following matrix: negative 197, 147, 76, 94, negative 108, 71, 59, 38, and negative 48. The next figure we're going to multiply by is the multiplicative inverse module of the determinant. First, you take the determinant and you divide that by 26, which is the amount of items we have in our encryption. This is doing long division. We will get 47 on top. 47 times 26 is 1,222. We'll subtract that and get 21 as our remainder. We will then subtract the remainder from our dividend and we will get 5. This is our modular multiplicative inverse. We will then multiply the matrix that we previously had and we will obtain this matrix. Negative 985, 735, 380, 470, negative 540, 355, 295, 170, and negative 240. You will then multiply the decryption matrix by the encoded message matrix. Note that the decryption matrix is the matrix we just gained from the previous slide. Similar to other matrix multiplication, you will take the row of the first and multiply by the column, and this will give you the first value here. And then so on and so forth. After you do the multiplication, you will take the modular 26 of that matrix to get the decrypted message matrix, as seen here. This is in terms of the alphabet that we have chosen to use to decrypt our message. The decrypted message matrix will be 12, 7, 12, 8, 26, 8, 24, 5, 19, 18, 11, and 4. If we refer back to our alphabetical assignment to numbers, A is equal to 0, B is equal to 1, we will obtain the matrix as M, H, M, I, A, I, Y, F, T, S, L, F, which, when we read it out, spells math is my life. This is the Matlab code, which we will use to obtain the decrypted message matrix, as we see here in yellow. This is the end of the video. If you have any questions, have fun.